Okay, you will do presentation. Good. Okay, no
Some
problem.
minutes later.
Okay, we will send later. Yeah.
Related to the digital technology of SMR safety and electrical power system development. And now we are going to listen next speaker, Sergey Souch and Andrei Borisenko. Sergey, you ready? Please.
Maybe I will present this.
Okay, Andrei.
Research, yes.
Сегодня мой должен был в это время докладывать, вообще-то говоря. 16:00.
We will continue with you, so Leonid, no worries about that. Yeah, you will be next one. Thanks. No worries about that. Andrei, how much time do you need for your presentation?
I think it will be 15 minutes.
Okay, great. Please go ahead, floor is yours.
Thank you very much. Dear ladies and gentlemen, I want to present our research, modeling of local power system development under conditions of military operations. First of all, small introduction. Determining of optimal structure of generating facilities is a very actual problem, and also in the context of intensive use of renewable energy sources. A new important factor for simulative development of generating equipment is a large-scale military operation. During last winter, Russian aggressors targeted large power plants and substations, and as a result, entire regions of Ukraine were left without electricity. The issue of military influence on the operation of energy system is considered by the investigations, which is particularly note that positive impact of the development of distributed generation, storage system, and smart grid technologies on the reliability of energy system. At the same time, the question of determining the influence of military threats on the change of operational modes and structure of generation's capacity remains open. The purpose of the study, of our study, is to create methods for justification the development of local grids, later LGM, which may be disconnected from the country's power system as a result of military aggression. Let's take a look at the models for the development of generating equipment. First of all, the volumes of electricity generated from renewable energy sources are uncontrollable and are determined by weather conditions, which significantly complicates the operation of the power system. As a result, traditional models for the development of generating equipments, here and after CP, are not suitable for practical applications in the context of significant volumes of electricity generating from renewable energy sources. In order to adequately predict the operating modes of generating equipment, unit commitment models, UCs, are used. These models take into account the startup and shutdown costs of the equipment, its maneuvering characteristics, limitations, and so on. The integration of unit commitment models to the traditional models for generation equipment development is carried out by two main methods. First method is a method of weak links, which consists in iteratively solving of CP problem with successive refinement of the operating modes of the generating units by solving unit commitment problem for the forecast period. By the second method of strong links, where the functionality of the integral CP and UCs problem of operating and development of generating capacity is respected by the sum of investment costs and the cost for operation of power units. And the large dimensional problem formulated as a mixed integer linear problem is solved by the special solvers. The second approach used for the proposed purposes of this study. Let's take a look on the structure of the mathematical model. Well, first of all, the detailed description of the model is not provided in the presentation because of the limited scope of the report. You can find a description of the model for optimizing local grid operation mode in the publication Mathematical Model of Flexible Microgrid Integrated into the Contour Grid. It's an open access article. So the objective function, it's a sum of costs, investment costs of small modular reactors, storage system and RES, operating costs for the generating equipment, net electricity flow to the upper level market, contour grid, and from that contour grid, compensation to consumers for undelivered volume of electricity. It's a result of restrictions. There are some constraints. First of all, balances for electricity production and consumption, states of power units, state of energy storage system, and volumes of electricity consumption. Also, there is the conditions of cycling, also state of power units and HESS, some conditions for initial number of power units, and for commissioning of new power units. Limitations in the form of inequality. Here is a limitation of the volume of investment, the introduction of new power units, electricity outflows and inflows limited by grid capacity, and also limitation on the power unit load. It's a limitation by the maximum achievable load, minimum achievable load, and also the speed of load growth and load drop. Also, we have the limitation for the ESCs, also maximum amount of energy storage, minimum amount, and also the speed of this amount change. Volume of consumer restriction, we have some maximum allowable amount of restriction, and also some conditions of cyclicity. Let's take a look on the object of study and computational experiment. The experience of Russian attack show that the main target of the attack was a powerful power station working on the organic fuel and big substations of the transmission system operator. And the peak of attack was during the peak of consumption of electricity and heat from the October 2022 to March 2023. As a result of the damage, the whole region of Ukraine remained without electricity. It was a period of 23rd of November, as far as I remember. And electricity shutdown schedules were introduced for other regions. To reflect the influence of military factors on the energy supply of the region of the country, a tentative local grid is considered. This local grid, of course, is a hypothetical local grid, covers the consumers located in a certain territory and the production electricity is supplied by renewable energy sources, wind farm and solar power plants, small modular reactors. We introduce here small modular reactors because they don't depend on the constantly supply of fuel and have a good maneuvering characteristic. Also, the construction of energy storage systems are foreseen. Under normal, peaceful conditions, the local grid operates synchronously with the contour grid. Depending on the price level on the wholesale market, local grid can act as a consumer or a producer of electricity for power system. Under the wartime conditions, every winter the local grid is disconnected from the national energy system and operates in an island mode. Here you can see the assumption that are the basis of the local grid model. Electricity consumption projection, initial LG capacities, capacity of interconnection, electricity price, transmission tariff, the cost of solar and wind power plant electricity, discount rate, ESS characteristic, and also specific capital cost for new equipment. The result of computational experiment. The mathematical models was implemented in IBM iLog CPLX Optimization Studio. First of all, let's take a look on the representative weekly load curves. You can see upper on the right. Here, red line is a production of solar power plants, and blue line is a production of wind power plants. As you see, local grid production is determined by solar power plants in summer period and by wind power plants in winter period. Lower you can see the capacity expansion for peaceful conditions on the left and capacity expansion for wartime conditions on the right. Under wartime, significant costs for compensations of consumers' losses because of restrictions lead to the expendency of commissioning more solar power plants, small modular reactors, and ESS. Here you can see a red line is a solar power plant. Here you can see in the war conditions much more solar power plants. Also, violet line is a new nuclear power plant, small modular reactor. You can see during a wartime condition we have 2 of such units, and green line is in ESS capacity. Here you can see on the right also some development of 100 megawatt development of such systems. At the same time, the volume of wind power plants capacity commissioning is reduced. You can compare blue line on the left and blue line on the right. Let's take a look on the operational mode of this local grid. On the right, you can see load graphs for peaceful conditions, and on the right, load graphs for wartime conditions. Here you can see demand load, operational load. Operational load is adjusted by the restriction of consumption, generation, and net supply. Net supply is generation adjusted by the net flow from the national grid and net flow from the ESS. On the right, you see shaded zones. It's a restriction of consumption, practically. So let's take a look on the what can we see from the analysis of this graph. Under peaceful conditions, the demand is covered in all the system modes. The LG production are determined by the solar power plants in summer and wind power plants in winter. In summer, a significant volume of electricity is sold to the wholesale market. In winter, for wartime conditions, local grid consumption is restricted due to the lack of capacity in the local grid and impossibility of obtaining electricity from the wholesale market. Critical operation modes for local grid are during the periods of the maximum load in winter time, when it is disconnecting from counter grid. In this mode, it's necessary to ensure sufficient flexibility of local grids and to minimize the disconnection of consumers. These requirements increase the capacity of small modular reactors and ESS. which determines the winter generation load curves. And also, as I talk about below, to limit the capacity of wind power plants. Finally, let's take a look on conclusions. Military operations not only lead to prominent change in the load modes of local grid, but also have a significant impact on the development of its generation capacity. The critical load modes of the local grids occurring during period of maximum electricity consumption. In order to ensure flexibility of the system, more intensive development of the maneuverable small modular reactors and ESS is taking place. At the same time, the development of wind power with uncontrollable generation in winter is limited. Despite the increased amount of generation coming into operation, it's necessary to limit electricity consumption in order to meet critical load of the local grid, of course, in the wartime. Given the essential impact of military operation on the operation conditions of electricity system and the development of their generating capacity, it's important for countries suffering from such threats to develop local grids that can support the vital activities of the communities. Thank you very much for your attention.
Okay, thanks, Andrei, for your presentation. Now we have time for question. Colleagues, do you have any question to Andrei? Oh, okay, Andrei, I have some very simple questions for you, if you don't mind.
Okay.
Your model, typically I know SMR is following some kind of economics of scale. So it means the more unit we build, the less price, operational cost, and all of the cost will be less. It's supposed to be in this way, at least new scale and all of the companies who are dealing with that, they claiming it would be less money for more units, right? My question is the following. Your model, does it take into account somehow the model of units which could be deployed somehow? Because you're dealing with the cost, right? In this case, unit, it's a little bit impact the cost. How you model incorporate the idea of the number of units for SMR particularly? Because I saw you took SMR as an example into your case, your case. Could you comment on that?
Yes, of course. Thank you very much for your question. It's much more deeper than it sounds, because first of all, it's necessary to compare the economical characteristic of standard nuclear power unit with SMR. And we understand that the cost of electricity from huge nuclear power station, like the size of Zaporizhzhia, will be much lower than SMR. So introduction of local grid will typically increase the cost of energy supply, first of all. But it's a price of, it's a cost of stability of electricity supply. Second one, of course, nobody will build, but anyway, we have, there is an example in the world of building of one unit nuclear power station. We have such stations, but normally the minimal quantity of nuclear power units is 2. And of course, the first unit is much more expensive than the second one. Of course, here is some question, because our model is hypothetic, and but here also some question. From the time of Soviet power system, we have a special, it is not a rule, but algorithm of activities. So in the case of emergency, the power system will be separated on the areas with the name is separated area. So the power system will be separated, have to be separated on the area with the power system, big power plant in the center. So it's necessary to check the net structure and the quantity on consumers, which will be covered by such region, and to estimate how many small modular reactors will be useful or reasonable to possess in this territory. But normally it will be 2 or more. Okay, and in our model, there is no, in this formulation, there is no difference of progressive change in costs depending on the quantity of small modular reactors. But the model could be improved. Thank you for your question.
Okay, could I ask one more simple question again?
Okay.
So, yeah, so for Ukraine, SMR deployment is a good prospect, right? And for us, for all of us, we need to understand how many units is enough. Is it, for you, it's like easy question? Could you model deal with that? I mean, could we, like using the model like that, could find the correct answer? Like, okay, so we need to deploy, let's say 5 SMR units, it would be enough. Or we need a little bit less or something like that. Because it's always about money, right? It's always about efforts which are being used to deploy something. And in this case, could we find this answer, like how many is enough in this case? For example, using your model and from your understanding of this situation, could you comment on that? Maybe you can give me a very short, brief answer, would you please?
Yes, okay. It's the purpose of this model to optimize, to have the instrument to optimize the mixture of capacities for the local grid. So the first step is to localize the volume of consumers and the architecture of this grid, and then it will be possible having the projection of consumption to calculate how many SMRs is necessary to build. But the second question, Sergei Evgenievich Sauch talked about it. The SMRs will be more expensive than standard nuclear units. So it's necessary from the side of regulator or from the side of government to introduce the financial and economical support for building of such units. So we can calculate, but how many of them will be built, it's a question of another level.
Okay. Anyway, thanks for your opinion about that. If we don't have any other question, let me invite next speaker.
Can I add a small addition?
Oh,
to
yes, sorry.
To this discussion.
Sorry, please.
I would like to underline the specific of this investigation. This investigation presented, first of all, in order to show the difference of the generation planning problem in new reality, in the reality of the military attacks on the power systems. And we showed that the adequacy of the planning dependent if we take into account these factors or reject it. When we thinking about peace all time in the future, of course, it is results must be rejected. But when we think about the future of the country and take into account the reality that we can observe now, unfortunately, we must take into account the influence of military actions on the and aggressions on the infrastructure, electricity infrastructure in Ukraine. And from this point of view, this investigation is very adequate without looking at the hypothetic structure of the investigated local grid presented here. Thank you.
Okay, thanks, Sergey, for your comments.
I have
Dmitry?
one question,
Okay.
please.
Okay, Dmitry.
Andrei, thank you very much for a very interesting report. My question is about small nuclear modular reactors. How we can protect these reactors from destruction as a result of missile attacks, for example?
You see, we have, maybe you better than me know the results of Russian attack of the energy power system. The reactor, nuclear reactor tool, is a very nice protect structure within a concrete structure with special iron. So it is protected from the aircraft fallen. But the main idea of Russian attack was to attack transformers and switch gears near the power station. Anyway, the capacity of one reactor is about 77 megawatts. Yes, it's near the figures that you mentioned before. Yes, so if it will be two reactors power stations, the capacity will be about 150 megawatts. Yes, so anyway, such structure with a lot of power station will be much reliable than standard one. But anyway, it will be the target for attacks. We have two variants of to increase reliability. First of all, small modular reactors have a higher passive defense system than traditional one. Yes, so potential damage for the territory will be lower in the case of emergency. And the second one is necessary to improve anti-aircraft system as for the attack. Speaking about local grids, as you see, small modular reactor is only the part of in the structure of generation. And so if we will find the optimal balance between small modular reactors, solar power plant, and storage system, it's possible to also increase the possibility of good supply of electricity for consumers. Thank you.
Thank you very much too.
And in addition, I would like to say that applied the rocket attack on a nuclear power plant means applied nuclear rockets, applied nuclear weapons. It's not depend where it happened, where you introduce this nuclear charge or use the nuclear power in order to destroy the big territory. It's the same. And the protection, this question is not the same as application to the power system, to power grid, to ordinary power station. It's not the same. The aggression about nuclear power plants is equal to nuclear weapons. It's the same.
Excuse me, one small addition. Speaking friendly, all we understand that this idea was the only reason of absence of attacks of Russians to the nuclear power stations of Ukraine.
Thank you very much.
I just have some comments about that. It's a very interesting topic, and I would like to ask Mikhail Stebinetsky about that. Mikhail, would, from your understanding, the current SMR technologies, SMR project, you familiar with, I guess, with all of them, are they protected against some kind of physical impact from missile, something like that? Could you comment on that if you, it would be appreciated? Okay, so maybe we can leave my question to Mikhail, because it's like coming directly to the current discussion, but we will keep this question for maybe next of the session. Okay, thanks again, Andrei and Sergey, for your presentation, and let me invite